Hello everyone and welcome to Digital System and FPGA tutorials. In this FPGA Verilog and Vivado tutorial, we explain how to save simulation data to files from Verilog and Vivado simulations. Motivation. The standard practice when developing and implementing FPGA algorithms is to first implement and test algorithms in MATLAB and Python. This is done since it is significantly easier to test algorithms in MATLAB or Python than in FPGAs. After MATLAB or Python simulations confirm that algorithms work as expected, the next stage is to implement them in Verilog and to simulate them in the Vivado development environment. The final stage is the FPGA implementation. During testing and simulation in Verilog and Vivado, it is often necessary to save simulation data to files such that the Verilog simulation data can be compared with the data generated in Python and MATLAB. Consequently, we need to know how to save Verilog simulation data to files. To summarize, the material presented in this tutorial is very important for developing and simulating algorithms in Verilog. As a test case and as a demonstration, we will implement a simple Verilog program that will perform bitwise complement of the provided sequence of the 2-bit binary numbers. And over here, you can see the Verilog module. Here's the plan and the outline. First, we will write the Verilog module. Then, we will write a Verilog simulation file or a test bench file. The Verilog simulation file will first load test data from a file. The test data is a 2-bit binary sequence that should be inverted by the Verilog module. And over here you can see the input data with the binary sequence. This binary sequence will be loaded by the simulation file, and our Verilog module will perform 2-bit complement and it will produce the output sequence. This output sequence will be saved to another file. Okay, let's start from scratch. The first step is to open Vivado. So click on Start and search for Vivado. And as you can see over here, I'm using Vivado 2024.1. However, you can use any other version of Vivado. The implementation principle will stay the same. So let's wait until Vivado opens. And let's wait for a while. Good. Let's create a project. Click on Create Project, click on Next, click on Next, click on Next, and over here, let's select a board. It really doesn't matter the board you will choose, since we will not upload the data to our board. I like to choose Nexus A7, since this board is often used in electrical engineering programs in the United States of America. Let's click on Next and click on Finish. Okay, the first step is to create our module. To do that, click over here on plus, make sure that Add or Create Design Sources is selected, click on Next, and click on Create File. I will call the file as test_module and click on OK, then Finish and click on OK and Yes. Now wait for a while, and after some time under this Design Sources folder, you will see our module. Double click on the module to open it, expand this window, erase the comment section, and let's start with coding. This module will have 2 ports. The name of the first port is input data, and the name of the second port is output data. Now let's make sure that we close the parentheses, and let's continue. Next, we need to declare that input data is an input port. To do that, we need to type this input, then we need to specify the port width. It will be a 2-bit port, and we need to say, that is, we need to write the name. The same thing should be done for the output data. It is an output port, it's a 2-bit output port, and let's specify the name. And over here, let's implement a simple equation that will perform the bitwise complement or the bitwise negation of the input data bits. So consequently, we need to write output data is equal to not or complement of the input data. And let's save this file and let's continue. The next step is to create a file that will contain the input binary sequence. So let's do that. I'm going to use a notepad to create the file. First of all, I will create a text document. I will call it as input.data. And then I will edit this file and I'm going to enter a sequence of binary numbers. The binary numbers should be 2-bit binary numbers, so let's start 0001 1011. Then let's repeat 0001 1011 and let's add 2 additional binary numbers 00 and 11. And let's save this file. Good. Let's close this file and let's go back to Vivado. Next, we need to tell to Vivado and Verilog where this source file is located. So let's do that. To do that, click on Design Sources, click on plus, make sure that Add or Create Design Sources is selected, click on Next, and click on Add Files. Over here, locate the folder in which the file is located. Here it is. And click over here and go all the way up and click on All Files and you will see your file. Click here and click OK and click on Finish. Good. The next step is to write our simulation. To do that, click here on Simulation Sources, then in Simulation Sources click on plus, then click on Add or Create Simulation Sources, click on Next, and click on Create File. I will call the file simply as simulation. And click on OK, and click on Finish, click OK once, and click on Yes. And then wait for a while until the file is created. Next, expand this menu, double-click on Simulation, and let's start creating our simulation. But before we do that, let's erase these comments. Then let's erase the parentheses and let's leave the semicolon. The first step is to declare the variables. First of all, we will need an integer for iterating through the input data file. I will call this integer as k. Then we will need another integer called file1. This integer will be used to open the file. Then we need to declare 2 registers. The first register is for the input data variable. That is, we need to define an equivalent variable to this variable over here. In our case, it should be register, so I need to type a register, then the length of the register should be 2-bit, and the name is input data. Then we need to declare an equivalent variable for the output data. So let's copy the variable name, and let's type var. The type should be var. It's a 2-bit var, and the name is output data. Of course, you don't need to use input data and output data for these 2 variables that should be connected to these 2 ports inside of our simulation file. You can use any other names. Later on, we will connect them. Next, we need to declare a clock variable. Consequently, we need to type register, and I will call it as clock. Next, we need to declare a register array that will store the input sequence from the file. To do that, we need to type reg for register, then we need to specify the bit width of every entry in the array, and then we need to specify the name of the array. And then we need to define how many entries we will store in the array. In this data array, I'm going to store 10 entries. Consequently, I need to write this. Why 10 entries? I'm storing 10 entries since my input file has 10 entries, and consequently, I will need a memory space with 10 elements to store the input data sequence. The next step is to define our clock. To define the clock, we need to type this, always. Then we need to type the half of the period of the clock. In my case, the half of the period will be 10 time units, and then I need to type clock is equal to complement of the previous value of the clock. This will create a pulse clock with the half of the period equal to 10 time units, and a time unit is 1 nanosecond. Consequently, the period of this clock will be 20 nanoseconds. Next, we need to define a unit under test. That is, we need to tell to this simulation file that we want to test our module. Consequently, let's go to the test module, copy the name, paste it here, and let's call the unit under the test simply as UUT. And let's close the parentheses and add semicolon. The first step is to connect input data and output data ports from our module with these two variables from our simulation. To do that, we go to our module, copy the name, type dot, then the name from the module, then the name from the simulation in parentheses. This will connect input data port from our module with the input data variable inside of our simulation. We do the same thing for the output data. And here it is. Good. We can continue. The next step is to define our simulation. To do that, we need to start the initial block. After that, we need to type begin, and then we need to end the block. So let's start. The first step is to initialize clock and to set it to 0 and to set k to 0. Then over here, we need to read the data from the file. Okay, to do that, first of all, let's make sure that the file is at the proper place. Here is the file, and you can see inside of this simulation folder there is a data files folder, and here's the file. To open and to read the file, we need to type this $, then read memb, standing for read member. Then we need to specify the exact name of our data file. It is input.data. Then we need to specify the array in which the data from this file will be stored. The name of the array is data. So let's copy it over here and let's add the semicolon. So what will happen now after this statement? All the numbers from this file will be read and they will be stored inside of the data array. Good. Let's continue. The next step is to open the file that will be used to save the simulation data. Consequently, let's use the file1 integer that's declared over here, and let's type file1 and then again $fopen. Then we need to name the file. Since the file doesn't exist, it will be created. I will call the file simply as save.data, and we open the file in the write mode. If there is some content in this file, that is, second time we run this simulation, the previous content will be overwritten. Okay, let's continue and let's type a comment over here, save, open the file for saving data. Good. Next, let's introduce a delay of 20 nanoseconds. Next, let's define a for loop. This for loop will go through the elements of the array data, and it will assign the elements to the input data. Then the module will invert the data, and then in the for loop we will store the data to our file. Again, the name of the file is save.data. So let's start. For we initialize k to 0, then we run the for loop until k is equal to 10, and over here we increment k. The structure of this for loop is very similar to MATLAB or to, for example, Python for loops or C for loops. In fact, Python doesn't have this type of for loops. Okay, so let's begin and let's end the for loop, and inside let's do this. First of all, let's type input data, and let's store in input data the value of data k. Okay, this will store the binary sequence in the input data. Then let's wait until the positive edge of the clock. To do that, we need to type at pos edge of the clock. What will happen over here? Since the clock is a train of pulses, we are going to wait until the rising edge of the clock is detected, and the code will then continue. So what do we do next? We need to save the data to our file. Consequently, let's type fdisplay. This function is used to save the data. Let's specify the file. It's file1. We are saving in the binary format, so let's type this. And what are we saving? We are actually saving output data. So let's copy output data from here, and let's add a semicolon. Good. Then what do we do next? We do this. Let me just align this. If k is equal to 9, that is, if we reach the end of our array, let's simply close the file. So we need to type this $, and fclose, and what are we closing? We're closing file 1, and that's it. Let's make sure that everything is done. Yes, we have two ends over here, so we have begin over here, then we have end over here, then we have another end from this begin statement, and that's it. Simple as that. And finally we end the module. Good. Let's save this file. Let's make sure that there are no errors over here, and let's run the simulation. To run the simulation, we simply need to click here, and this should run the simulation. Click here and run behavioral simulation, and let's see what will happen. And here it is. Okay. Over here you can see the timing diagram, and let's just briefly inspect the timing diagram. Move this slider until the beginning, then zoom out, press and hold Control, and use the middle mouse button to zoom out and to see the sequences. Over here in this row, let me just expand, that is, in this row you can see the input data. Let's click here, do the right click, select the base to be binary. So this is our input data, and let's see the output data. Again, select the output data, right click, and select binary base. And we can see that the output data is being inverted, since over here you can see 1, 1, output is 0, 0, 0, 0, 1, 1, etc. Good. However, let's check that the output data is correctly saved in the file. How to do that? Well, we need to locate the folder in which our simulation stores the files. So let's do that. In my case, I need to go back to my C folder. Then over here in users and my username, you'll find the files, or better to say the folders. These are Vivado folders. This is my current project. Click on simulation, click on sim1, behavior, xsim, and if you click here on date modified, you will see the file. Let's open the file. Here. And as a final check, let's compare the input and output files. Here's our output file, here's the input file, this is the input sequence, and this is the output sequence. 0, 0 in the input file and 1, 1 in the output file. Correct. Then let's pick this element 1, 1, 0, 0. Perfect. and you can convince yourself that everything is properly inverted and saved. And in this way, we can save the simulation data to a file. Okay, that's all for today, and thanks for watching.